Hi everyone, it's 12:30, so we're gonna start. Today we have Nathan Klein on the IAM, and he's gonna be presenting in for.
Okay, yeah, thanks a lot for having me. I'm gonna keep things a little bit more basic and do a little bit more intro because, you know, it's lunchtime. So definitely ask me questions as much as you can. Oh. Something's making noise, I think it was me. Okay, yeah, and we're talking about thin trees for laminar families, and this is joint work with Neil Olver. Okay, so I'm gonna jump right into it and define thin trees. So given a graph and a tree of that graph, so in this example, we have a complete graph and the tree is the star given by these red edges. If delta of S is the set of edges that have exactly one endpoint in a set S of vertices, we say a spanning tree is alpha thin if on every cut of that graph, the number of edges the tree has in the cut is the most an alpha fraction of the total number of edges in that cut. Okay, so this is a little bit of a mouthful, but just to say it again, like we have an exponential number of constraints to certify that a tree is alpha thin for some alpha between 0 and 1. And you're alpha thin if all these constraints are met for every set S. So just to check, we're all on the same page. Does anyone see what the smallest alpha we can choose for this tree and this graph is? Should be some number between 0 and 1. Yeah.
1?
It's 1, yeah, thanks a lot. So exactly, so if you look at this vertex here, the tree contains every edge in the cut, right? So for the constraint consisting of this vertex, the left and the right-hand side of these equations are the same, and so we're forced to choose alpha as 1. On the right is it's much more difficult to see kind of what the thinness is, but does anyone have a guess for the smallest alpha we can choose on this graph? 1 over n, yeah, thank you. So this is 1 over n, and actually in general, we don't even know how to check the thinness of a tree in polynomial time. So this was a bit mean for me to ask you, but it is true that this is actually something about a 2 over n, like thin tree. Okay. And we say the tree is thin, I think, kind of because, well, if you delete a thin tree for alpha close to 0 from a graph, it sort of means that the number of edges in every cut does not change very much, right? So, you know, a 1 thin tree, if you delete this from your graph, the structure changes a lot, right? Suddenly the graph becomes disconnected. But if I delete this tree from the graph, there are not many kind of global properties that change. So I think that's the intuition maybe for why it's called a thin tree. Okay, and so what we're interested in is finding thin trees for graphs with alpha kind of close to 0. And there's a conjecture from Goddyn in 2004, which is that every k-edge connected graph, so every graph that has at least k edges going across every cut, should have a tree that has that is order 1 over k thin. Yeah. Yeah, great question. Right. So if you ask for spectral thinness, that's a strictly stronger property, and actually it's false. Yeah, it's false. So yeah. So if you want to solve the spectral version of this question, you can. Yeah. Could be. Yeah, I would have to think about it. But yeah. Yeah, great question. Yeah, I want to say if we don't get to the details at the end, that's okay. I want to just focus on the introductory stuff. So the more questions, the better. Okay, so Goddyn conjectured that actually every k-edge connected graph has an order 1 over k thin tree. And this is like the best you could do, right? Because if you have a cut with k edges, the tree has to take at least 1 of them. So you certainly can't do better than this. So this is called the strong thin tree conjecture. And you can see it's true on the complete graph. right? Because here, like, k was n-1, and we found a thin tree. And actually, what Goddyn conjectured was something much weaker, which is still open. So both of these are open. That there's just some function that goes to 0 as k grows, such that every k-edge connected graph has an f of k thin tree. Right. So the strong version is just that, like, the function is going to 0 as fast as possible. It's 1 over k. But in general, we would be happy with like 1 over log k, 1 over log k, whatever. Just something that goes to 0. Okay, great. So I think the question is very interesting on its own. But actually, this has some very nice implications, the strong version. So it turns out that if you can find algorithmically a 1 over k thin tree, then you get a constant factor approximation algorithm for the asymmetric traveling salesperson problem. And you also prove a weak version of Jaeger's conjecture on nowhere 0 flows. And you also can solve various problems on spanning trees and kind of cut constrained spanning trees. Yes, yeah. Actually, this one I should check, but this one you definitely need the strong version. And I think, yeah, so I guess this one you definitely need the strong version. The other versions may still be interesting for certain functions f. So yeah, good question. Okay, so it turns out that since Goddyn's conjecture, both of these things have been resolved by very different methods. But I think, it would still be very nice, for example, to find another algorithm for ATSP. And even the question on its own, algorithmic or not, I think is really interesting. Okay, so what's known about this problem? We know that there are, from 2010 work by Asadpour et al., we know that there are log n over log n times k thin trees. So we have some function that depends on n, which we don't want, but at least the dependence is not so large. We know that every graph has a thin tree where alpha depends on the maximum effective resistance of the graph. This is from Marcus Fielmann and Srivastava's work on the Caddison-Singer problem. And we also know that this is not algorithmic, but there are poly log n over k thin trees, and this is sort of combining some previous work with this Caddison-Singer problem work. But we actually do know it's true for some special graphs. So we know it's true for planar and bounded genus graphs, and it's also true for edge transitive graphs. And the edge transitive graph you can see is just the corollary of the maximum effective resistance being small, if you're familiar with that at least. If not, don't worry about it. Okay, so you can see that like all these papers are about 10 years old or more. So there really hasn't been much progress kind of on the general problem. So what are we to do? Maybe we should look at some special cases. Okay, so what if we restrict our attention to not all the cuts, right? The thin tree conjecture, a thin tree requires you to be thin on like this exponential set of constraints, so every cut of the graph, which again, we don't even know how to check thinness in polynomial time. So maybe, maybe we can do better if we just ask about a subset of the cuts. So we say that a tree is alpha thin for some family of cuts C, if for every cut in that family, we obey the thinness condition, right? Okay, so then we can actually prove some things. So we know that the strong form of the conjecture holds if we just want the family of cuts we care about to be the set of vertices. Okay. We also know it's true if we only care about a chain of cuts, so a family of cuts in which for any pair of them, one is a subset of the other. And we can also sort of do optimization over these kinds of trees. We can find the cheapest tree that's thin on the vertex set and 1 plus epsilon approximation for a thin tree on a chain of cuts. So we sort of, these problems are resolved sort of very robustly. But an open question in this area is, can we obtain a thin tree on a laminar family of cuts, right? So we say a set of cuts is laminar if for any pair of sets, they're either disjoint or one contains the other. And this problem has been studied a little bit, and we know an additive violation of log n, or log of the size of the family, which can be n. And we're interested in something that does not depend on n. Okay. And I want to say just a little bit why we care about laminar families. So first, sort of as a constraint problem, it's interesting because it allows edges to be in arbitrarily many constraints, right? Like omega of n constraints. In the vertex case, every edge is only in 2 constraints, right? And then also, like if you compare it to the chain case, the sort of width of the family, so maybe defined as like the number of children of a constraint, can also be arbitrarily large. But I think the main motivation is actually that laminar families arise a lot from uncrossing type arguments. So what does that mean? It sort of says that if you have some collection of constraints, often you can show that it's enough to satisfy some laminar family of constraints to satisfy all of the constraints. So for example, if you look at the set of tight constraints in an extreme point solution to the subtoroid linear program for TSP, this is spanned by some laminar family of constraints. And you can generalize this to sort of many graph problems. So these are objects that kind of arise often when we're studying optimization problems over graphs. And so it's good to know sort of how to deal with them. Okay, so this is what we prove. We show that actually you can do this on laminar families of cuts, and you can find these trees in polynomial time. So previous work showed you how to do it for the vertices and for chains, and now we sort of generalize this and allow you to add more cuts as well. Okay. And before I get started, I want to share a quote I like from Brian Eno. So he said, gardening, not architecture. And I think probably, he meant something like, when you're working on a creative problem, don't kind of plan everything out, let things grow organically. I think it's good advice, but I think for theoreticians, we should take his quote in a different direction. I think we should work on problems about plants. So join me, thin trees, sunflowers, cactus graphs. Okay, all right, let's get started. So first I want to tell you about how to translate this question about thin trees onto really a problem about rounding a solution to a linear program. So I come from approximation algorithms, and so I really like to round linear programs. And so this is how I want to frame the problem. Okay, so it turns out this is equivalent to the strong thin tree conjecture. I give you a point in the spanning tree polytope, so some fractional spanning tree. And now I ask you to find a tree which has at most a constant times the number of edges the fractional tree had in every cut. So just as a reminder, this is the spanning tree polytope. We want that for all partitions of the vertices. So here's a partition of size 4. We want that this fractional tree has at least the size of the partition minus 1 edges crossing this partition. So if I sum the red edges here, it should be at least 3. And this describes the dominant of the polytope. And if you add this green constraint, then you're inside the polytope. We're not going to worry too much about this distinction. And you can notice that a sufficient condition for being in the dominant of this polytope is that every cut has at least 2 edges crossing it. Because if you look at the left-hand side here, this is just going to sum over all the partitions. So this is going to be the size of P times 2, which will sum to P. And this is at least the size of P minus 1. So it's enough to get in the dominant just to set every edge, just to satisfy this condition that every cut has at least 2 edges crossing it. Okay, so this is now like a rounding problem, right? We have a fractional spanning tree, and I want to round it so that we don't have too many more edges than the fractional spanning tree on every cut. Let me prove that this implies the thin tree conjecture. So let G be some k-edge connected graph. This is like the input to our problem. Then I'm going to set xe to be 2 over k for every edge in this graph. So I went from k-edge connectivity, and now under this weight vector of x, I get 2-edge connectivity, right? So we're in the dominant of this polytope. But now apply this sort of pseudo theorem, or this thing we're supposing is true, and produce a tree where on every cut you have at most order 1 times the x value of edges crossing that cut. Well, we know that now the number of edges the tree has in that cut is at most order 1 times the x value, but the x value is just 2 over k for every edge, so it's 2 over k times the number of edges in that cut. So yeah, so any questions about this? So basically, by just setting the LP value to be 2 over k, we're now saying that up to order 1, it's enough to have the same amount of, like since we've put k in the denominator here, it's enough to have order 1 times this 2 over k. Okay, so now we can actually prove a rounding theorem, and this is what we do. So we show that given a point in the spanning tree polytope and some laminar family of cuts, we can actually find a tree. We can round this point x to an integral tree, such that the number of edges you have in every cut is at most 22 times the x value crossing that cut. And also we get to do something with cost, so we increase the cost by a factor of at most 5. Yeah. I would need to think about that. Yeah. Mm-hmm. Mm-hmm. Yes, right. Yeah, so it's easy to get, yeah. Okay. Yeah, so the thing is, like a laminar family over a set of elements is different than over the set of edges. So like, if you think of the sets as containing edges, I'm guessing the VC dimension is large. Yeah, but yeah, we can. Yeah, that's a good question. Yeah, I think it should be large. Okay. Other questions? All right. So I'm gonna take a step back and talk about the technique of iterative relaxation, kind of from scratch. And this is going to be the main technique we use in the proof. So you can start over now if you got lost. All right, so what is iterative relaxation? So consider just some linear program. You have n variables, x1 through xn, and you have some trivial constraints that say that these variables should all be between 0 and 1. So there's some kind of box constraints that you're have to be inside of. And then we have some number of non-trivial constraints, say m non-trivial constraints. For example, we have 4 in this picture. Okay, then we know that in any basic feasible or extreme point solution to this LP, so if we're at a vertex of this polytope, there must be exactly n or dimension many linearly independent constraints that are met with equality that uniquely define this vertex, right? This is a very well-known fact. So in 2 dimensions, like if you're optimizing some function over this polytope, you're going to get sort of 2 constraints that give you your vertex. And here's a simple observation. Okay, if n is larger than m, then at any vertex, there's always going to be some trivial active constraint. So you're going to have to use one of the sides of this box to get a vertex. Okay, so if n is greater than m, in this case, we're in 2 dimensions, so it means that there's only 1 constraint. And now if we optimize over this polytope, we're going to get some vertex which intersects a box constraint. In other words, whenever this criteria holds, there's always going to be some variable set to 0 or 1. And this simple idea is the basis of the technique of iterative relaxation. So here's the algorithm. This is just for a generic linear program with these box constraints. Solve the LP. If there exists a variable that's set to 0 or 1, delete it or fix it essentially to be 0 or 1 for the rest of the algorithm, and then update the constraints. Otherwise, we're going to have n linearly independent tight constraints that define my vertex. And we're going to find one that for some reason it's okay to delete. And we'll keep going. This is the whole framework. So let me give you an example. So case 1, we hit a face of the box constraints, right? Okay, in this case, I'm going to fix x1 to be 0 and continue rounding on this lower dimensional space. So in this case, I'm just going to continue rounding on this line. Or if you want a slightly better example, here, maybe we optimize and we find this vertex. Now we're going to optimize over this triangle, this lower dimensional face. Right? Yeah. Sorry? Oh, okay. So the vertex is just going to be on a face corresponding to whether it's 0 or 1. Of just the current fractional solution. Yeah. Yeah. So I just look at this vertex, and if it's set to 0, then I'm going to fix it to be 0, and I keep going. Okay. And then in case 2, we hit n linearly independent tight constraints. So we're not at a constraint of the box. Then we have some procedure that allows us to delete one of these constraints. So this procedure, which is really the whole input to my procedure, is just going to find this maybe green constraint and delete it. Then I re-optimize. Maybe now I hit case 1, and I continue. And as long as I can always, whenever I'm in case 2, as long as I can drop some constraint, I'm always going to terminate with an integral solution. So it's a very simple idea, but it's extremely powerful. What do you mean should, I guess? Yeah. Yeah, so I'm optimizing this direction. Essentially, what I'm saying is this is just some generic procedure, and the input to the iterative relaxation procedure is going to be something that says when we're in this situation, there's going to be a constraint that's okay to delete. This is like the direction we're optimizing in. So before, I got stuck here, but now I'm going to get stuck like over here. Does that make sense? Or yeah, right. I'm always going to be optimized at some vertex. So let me know if it doesn't become clear. I'm going to say a little more. Yeah. Other questions? Yeah. Okay, so as I sort of just said, like the core of any iterative relaxation argument is really just to show that in case 2, there's some constraint that's okay to drop. So it can only, if I'm trying to minimize, let's say this is the direction. Yeah, I should have had a better direction. This is my fault, but if I'm trying to minimize, then dropping constraints will only let me make it smaller, right? Yeah, sorry. Okay, good. That was the, okay. Yeah, so let's think I'm trying to minimize the sum of x1 and x2 in this example. Yeah, so then every time I drop a constraint, my objective can only decrease. Yeah, so what you're losing, is that you're not going to satisfy all the constraints exactly. When I drop a constraint, I no longer guarantee that I satisfy it. Yeah, but in the end, this procedure is going to give me something that costs no more than the optimal integral solution, but my error is going to be how far away I am from the constraints. So yeah, so this is the key, sort of showing just when it's okay to drop a constraint, and basically there's two things that you can use. So one reason you may drop a constraint is if many variables have been set to 0 or 1, and sort of knowing that information means that your constraint is already approximately satisfied. That's possible. Or the other possibility is that maybe your constraint is sort of approximately implied by the constraints that remain. So these are the sort of two settings in which you allow yourself to delete a constraint. And then you can make progress. So let me show you this in action. And I'm going to prove this theorem that we've known for a long time, which is that given a point in the spanning tree polytope, you can find a spanning tree that has at most 5 times the number of edges that a fractional spanning tree had on every vertex. Okay, so here's the proof. It's very simple, and it follows this framework exactly. So you solve your linear program, you have some bound on every vertex corresponding to the original x value on that vertex. And then whenever you see an edge that's set to 1, you update the constraints, you add it to the tree. Whenever you see an edge set to 0, you delete it from the graph. And then here's the only interesting thing. This is our procedure for telling us when we can remove a constraint. You remove a constraint if the number of edges less adjacent to that vertex in the graph is at most 4. And I claim that as long as this algorithm terminates, we're going to get a spanning tree with degree at most x of delta v plus 4, right? Because when do I violate this constraint in terms of the number of edges in the spanning tree? I violate it only after I've deleted the constraint corresponding to that vertex. But the moment in which I delete that constraint, I'm on some face of the polytope where there's only 4 edges remaining in the graph. Everything else has already been set to 0 or 1. So this can increase by at most 4. So that's the idea. So I just have to show you that this algorithm actually terminates, and then we're done. Okay, so suppose that 1 and 2 don't occur, so every edge is between 0 and 1. And let's say we're in L dimensions, so there are L edges remaining. Okay, that means that there must be L, or dimension many, linearly independent tight constraints that come from the spanning tree polytope and come from these vertex constraints. So we're in this setting, case 2. And now there's a theorem of Lau and Singh which uses uncrossing techniques. I'm not going to show it here, but it's really quite nice and not too hard. They show that if you're in L dimensions and you have constraints coming from a matroid polytope, or in this case, the spanning tree polytope, at most L over 2 or dimension over 2 linearly independent tight constraints can come from that polytope. So I have some constraints corresponding to the spanning tree and some constraints corresponding to the vertices, and at most half of them come from the spanning tree. That's what this says. So if we're in this situation, it must be that the remaining dimension over 2 constraints come from the vertices. And now we just want to show that condition 3 is going to occur. And to demonstrate this, all we need to say is that, okay, if every vertex has degree at least 5 in the remaining graph, then there are strictly fewer than L over 2 vertex constraints remaining at all. This is certainly sufficient, right? Because I have to have at least L over 2 constraints to sort of not intersect the face of the cube. So this would give me a contradiction and show me that one of these conditions must have occurred. That makes sense? Okay. So this is just an easy graph theory problem. It says that if you have a graph and every vertex has degree at least 5, then the number of vertices is strictly less than half the number of edges, right? So this is easy to see. Let's just prove it. So every vertex which has a constraint has degree at least 5. And now the sum of the degree of these vertices is at most twice the number of edges. But now if there are some k vertices that are active, they each have degree at least 5. So that's a lower bound on the degree sum. But 2L was an upper bound. So k is strictly less than L over 2, right? So this gives the theorem. I think is really nice. And it can be strengthened a bit. So this is a result from Lau and Singh. That if you have a point x in the spanning tree polytope, you can round it to a spanning tree of no greater cost than x. And you violate all these vertex constraints by at most an additive 1. You just strengthen, sort of tighten up the proof a bit, and you get this. Okay. Great. So we want to apply this for our problem. This iterative relaxation type procedure. It turns out there's an issue. So I'm going to start with a positive thing. It turns out that their approach very easily generalizes to any matroid. If you don't know matroids, just stick to spanning trees. But yeah, matroid is just some generalization of spanning trees. So they prove that given a point in a matroid polytope and some sets of elements, E1 through ET, such that no element appears in more than delta of those sets, there's always a basis of that matroid, which has at most the number of edges that X, the number of elements that X had, so fractionally, plus delta minus 1. So for spanning trees, these E1 through ET were just the vertices, sets of edges adjacent to each vertex, and delta would have been 2. So this gave you the plus 2 minus 1, the plus 1 bound. And the proof is essentially exactly the same for spanning trees and for any other matroid. Okay, so everything generalizes immediately. And so you can try to apply this theorem for laminar families, and it fails because in general, edges can be in as many as n sets. And now here comes the annoying thing, is that it turns out if you try to generalize this claim to matroids, it's false. So there exists a point in X in a matroid polytope whose ground set is the edges of a graph. And there's even a chain of constraints over the graph, such that for any basis of the matroid, we get a lower bound of like log n over log n. So my point is just that iterative relaxation frameworks generally do not really see the difference between different matroids. And if we want to prove the thin tree conjecture for laminar families, it's false for other matroids. So if we want to use this technique, we're going to really have to use the fact that we have a spanning tree and not some other matroid. So that's the challenge. And what we're going to do is, so yes, we're going to exploit the fact we have a spanning tree. And what we're going to do is sort of first find a subclass of points that iterative relaxation works on for any matroid. And then we're going to reduce to a point in this subclass, sort of using the fact that we have spanning trees. And the special subclass that we're working on is, we'll say a point X in a matroid polytope is tight for a laminar family L. If for every set in this laminar family, if I sum the X value of the edges that remain inside this set, that's equal to the rank of the elements in this set. So for spanning trees, the rank of the elements inside a set S is just the size of the maximum size forest of this subgraph. So somehow this is sort of saying like, we have a point X where we've somehow aligned the matroid and this laminar family. So you can think of. So in the remainder, we're going to prove two theorems. First one is that for a point in the spanning tree polytope in a laminar family L, there exists a point X prime in the spanning tree polytope and some laminar family L prime, such that X prime is tight for L prime. So to base this definition, where the laminar family and the spanning tree, the point in the spanning tree polytope are kind of aligned somehow. And then second, we're going to show that it's enough to solve the problem on X prime and L prime, and you lose sort of at most a constant when you go back to X and L. This is like what I mean by reducing to this case. And this theorem is not true for general matroids. And then we're going to prove that you can do iterative relaxation on sets of points that are tight for L. And this will work for any matroid. So this is sort of the framework that we're working with. And I'll start with this reduction to tight instances first. Right? So I'm going to prove this one first. So is the setup clear? Yeah. All right. So a key definition is a deficient cut. So we're starting with this laminar family. And we'll say a set in the laminar family is deficient if there exists some set A such that the number of edges going between the two sides is strictly less than 1/4. So this is not deficient because this is a 1/2 edge connected graph. This would be deficient because this cut has only 1/8. And now we're going to use this to prove this theorem. So first, I'm going to show you how to, given your initial point X in your laminar family L produce this X prime and L prime. All right, so the idea is while there exists some deficient cut, choose a minimal one in the laminar family. So say this S is a minimal cut in the laminar family that's deficient. Then let A be some set that sort of witnesses that S is deficient. Now I'm going to delete S from the laminar family and add A and S minus A to the family. So if I start with some S, which is deficient, here is some cut that sort of witnesses this deficiency. A, sorry, this is a child of S. Now I'm going to add A and S minus A to the family and delete S. This is the algorithm. Yeah, I'm always going to be adding, sort of deleting sets and then adding like children of those sets. Yeah. Yeah, so I'm not sure what you mean by refined, but you can add sets that were not originally in the family. I'm not sure. So S can have children as long as those children are not deficient. Yeah. So kind of, but we're like building this from the bottom up. So yeah. Okay, so this is the algorithm, and certainly as long as it terminates, which it certainly will, because we keep deleting sets and adding their children, we're gonna get a family which is not deficient. So none of the cuts will be deficient. Okay, and that means that if we scale the edges inside every set by a factor of 8, we're gonna have at least the size of S minus 1 edges inside. This is because we know that inside every cut, we're a quarter edge connected because we're not deficient. So if I scale by a factor 8, we're now 2 edge connected. And remember from the beginning, this says that we're in the dominant of the spanning tree polytope. So this means that for every set, we're at least kind of above this criteria. We have at least as much as we need in order to be tight for L. And I'm not going to go through the proof, but it's not too hard to prove that given this scaled point, there's some point X prime in the spanning tree polytope, which is actually tight for L prime and is dominated by 8 times X. You kind of start with this point that's not too deficient, you scale it up, and now you can actually find a point that's dominated by 8X. Okay. So that's how we get X prime and L prime. And now we want to show that it's actually enough to solve the problem on X prime and L prime. Okay, so why is this true? So for any cut S, we've kind of split it into a bunch of disjoint pieces, right? Kind of maybe S was split into A and S minus A, and so on and so forth. And now we have a bunch of sets that together compose S. And here's the key fact is that every time you split a set into 2 pieces, we know that the maximum of their values of, let's say, S1 and S2 is at most the value of S minus 1/2. This should be kind of intuitive. They shared at most 1/4. So if I sum these two, their value is at most half plus the original cut. And each of these things is at least 1. So therefore, each of them is at most X of delta of S minus 1/2. So I'm kind of going down this tree, and every time the max is decreasing by a little bit. So therefore, the number of times you split is at most twice times the original X value of the cut. Furthermore, every time you split, you only increase the X value of the children by 1/2 due to this inequality. So let's look at the X value of the sum of the children. This is at most what we started with, plus every time we split, we add 1/2, and the number of times we split is at most twice times X of delta of S. Therefore, if I sum the X prime values on these cuts, I get at most 8 times 2X delta of S, which is 16. So I sort of started with my cut S. And now, even if I sum the x prime value of all the children, I increase things by a factor of almost 16. So this says that whenever as long as I get a sort of thin tree with respect to all of these subsets, S will be thin as well. Because whenever I have an edge in an SI, whenever I have an edge in S, it's going to be contained in at least one of the SIs. Okay. So this finishes this theorem. Now I'll just quickly say about how we do iterative relaxation on these tight instances. Let's go back to this framework. Okay. So we're gonna go back to the same idea as for this degree bounded spanning tree problem. And we'll let these bounds be equal to the ceiling of x of delta of S for every set in the laminar family. And now we'll iteratively find an extreme point where we're going to remain in the matroid polytope. This is true for all matroids, but you could also just think of the spanning tree polytope. And we obey all the bounds for all the sets in our laminar family, and we're going to remain tight for L. As before, if an edge is 0, we'll delete it. If it's 1, we'll put it in our spanning tree and kind of continue. And now here's the sort of meat, which is telling you when to drop a constraint. The first thing is very similar to the bounded degree spanning tree case. It says that if there are not too many edges remaining, then it's safe to drop the constraint. So in this case, if there's at most 7 edges remaining in some cut, then you know you're going to get at most 7 extra edges beyond what you currently have. So it's safe to drop, right? This is where the 7 comes from in this theorem. And now there are 2 other conditions, which are a bit different. Let's look at the first one. It says that if S has exactly one maximal child, S prime, in the laminar family of tight constraints, and the delta of S prime, so these edges are a subset of delta of S, and the difference between these 2 sets contains at most 3 edges, then it's safe to drop S. So this is the version which says that basically S is implied by the existing constraints, approximately implied by the existing constraints. And the reason is that, well, S and S prime are tight. So x of delta of S is BS is equal to BS, that should be BS. And x of delta of S prime is equal to BS prime. And furthermore, these cuts aren't equal because they're linearly independent. And delta of S prime is a subset of delta of S. So that means that the bound on S is strictly larger than the bound on S prime. So it must be at least 1 larger than S prime. But now, as long as I satisfy S prime, if I have at most 7 times BS prime edges, well, now I'm going to get at most 3 edges more than S prime. But my bound was 1 larger. So it's safe to drop S. It's approximately implied by S prime. This is sort of the second regime. Okay, so the third constraint is very similar to the second one. And now we want to show is similar to before, that as long as every edge is between 0 and 1, one of these 3 things must have happened. So as before, suppose for a contradiction that none of these things happen, and there are some L edges. And we'll use this L over 2 for the spanning tree constraints, or the matroid constraints in general. And now we just want to show that if none of these conditions hold, then the size of the linearly independent tight constraints coming from the laminar family is strictly less than L over 2. Which is the same as saying 4 times the size of this family is at most 2L, right? And we'll prove this using a token counting argument, which is sort of standard in iterative relaxation. We're going to give every edge 2 tokens, and these edges will distribute their tokens to the sets in this family. And we'll prove that every set gets at least 4 tokens, and there's some token left over, right? So this is just a way of proving this inequality. I'm just counting things. And the token assignment scheme is every edge will give a token to the smallest set that contains U. And to the smallest set that contains V for every edge E equals UV. And now we know that every minimal set in the family has at least 8 edges because we dropped things with fewer than 8 edges. And so it has at least 8 tokens. And we only need 4 tokens. So what we can do is sort of keep 4 tokens and promote the rest to our parent. So here's the induction hypothesis. I can keep 4 and I can give 4 to my parent. The base case is every minimal set. Every minimal set has 8 edges, so we're good. And now let's do the inductive step. Okay, so let S in this laminar family have some children S1 through Sk. S is going to get 4k tokens from its children inductively. So if k is at least 2, we're actually done. Because you're going to get at least 8 tokens, you can keep 4 and keep giving 4 to your parent and keep going. So let's show this in a picture, right? We start at the bottom, we have 8 tokens for every minimal set. We can give 4 to our parent, and so on and so forth, but we get stuck when a set only has 1 child. So what do we do here? This is kind of like a pyramid scheme, right? So as long as you can keep getting 2 more people to join your scheme, then you're happy. But if you only get 1 more person, like, you're in trouble. Yeah, Paul Beam suggested the same. I think it's good. But it actually comes up very often in iterative rounding that there's only really one troublesome case, which is when you sort of have 1 child. So let's just show this step. And so far, I have not used anything about being tight for a laminar family. So this would work for general matroids. Okay. And the main thing I'm going to tell you, which is just that this property that X is tight for L is exactly what makes this case work. This would have failed for general matroids and general laminar families, but the fact that we're tight for L is just going to make the case where you have 1 child work. That's the whole idea. Okay, so first let's do the case in which, so first, remember kind of our rules. And we know that first let's check this case where sort of S prime has a subset of the edges of S. Then by this rule, there's at least 4 edges in the symmetric difference, because if there were 3, I would have dropped this set. But then each of these edges, the smallest set containing 1 other endpoints is S. So we're going to get 4 fresh tokens, because remember, an edge gave 1 token to the smallest endpoint, smallest set in L containing U, and the smallest set containing V. So here we're done. And the same thing is true if delta of S is a subset of delta of S prime. So this is the only hard case. And this is the only case we're going to use that X is tight for L. So when you have exactly 1 child, and neither set is a subset of the other. And the thing that could have gone wrong is there's exactly 1 edge here and exactly 1 edge here, because then I would only get 2 tokens, not 4. And this is exactly what breaks in the general matroid case. And now we're going to use that. We know since X is tight for L, the sum of the edges that lie inside S sums to an integer. So you cannot just have 1 fractional edge inside. You have to have at least 2. And it turns out either they have this structure, in which case this 3rd edge gives you 2 tokens because S is the minimal set containing U and V, or you have sort of 4 extra edges. And I don't need to go into the details, but basically it's just this condition that you have to sum to an integer inside that fixes this case. And for the last sort of token, right, we have that the largest set in the family had 8 tokens and it doesn't have a parent. So there's some token left over, and that says that this inequality is strict. Okay, so we get this theorem. We can round and lose a factor of almost 7. And so kind of multiplying these 2 things together, you get a violation of 112. And if you're, and this gives us our main result. And if you're a bit more careful, you can get this 112 down to a 22, which gives us a 44 over k thin tree for every set in this laminar family. And we also can solve this kind of optimization version of the problem, which says we won't increase the costs of the spanning tree by very much. You sort of lose a factor of almost 5. So let me just kind of recap what we did. I defined the thin tree problem and sort of its statement as a rounding problem. I told you about iterative rounding and a simple proof for bounded degree spanning trees. Then I told you that iterative rounding generally kind of works for all matroids, but the claim we want to prove is false for all matroids. So we kind of did this two-step thing. First, we reduced to a special class of points, which only works for spanning trees. And then we proved that iterative rounding works on this class of points. I think this sort of reduction step is maybe a bit new. And I think also the way that we did this iterative rounding, in which we allow constraints to be approximately implied by existing constraints, is also a bit new. So here's some open questions. The biggest one, obviously, is we want to prove or disprove the thin tree conjecture. Maybe this gives some evidence, maybe it doesn't, I don't know. The second open question is we get a 5 approximation for the cost. We want to solve the optimization version of this problem. And we can get it down to 2 plus epsilon, but I don't know how to get it down to like a 1 plus epsilon or a 1. I think this is a very approachable open problem. Another nice question is sort of how can this result be generalized? Maybe we have 2 laminar families. Can we still do it, right? Slowly ramp up, maybe eventually we can get to the thin tree conjecture. And open question number 4 is, well, we know that the thin tree conjecture implies a constant factor for ATSP. But as I said, laminar families really appear in a lot of network design problems. So maybe somehow this result is still useful for ATSP. So thanks a lot. Yeah. Yeah.
Is there anything hidden here that would be hard to do algorithmically, or does this really give us the pretty efficient method to compute these problems?
No, yeah, this is very direct. So it's actually pretty fast, I guess, as long as you can re-optimize your LP quickly. But really, you're just solving an LP. You're looking at this vertex and you're saying, can I drop some of these constraints? And they're at most like 2n constraints to begin with. So you can't have that many iterations. The other thing that can happen is you set a variable to 0 or 1. That can happen at most n minus, yeah, that can happen at most like number of edges minus times. So yeah, it's actually very simple algorithmically and pretty fast. Yeah.
Okay, is there no further question? I think the speaker.
Thanks.